the equilibrium constant. So at equilibrium, the rates of the forward reaction and reverse reaction are equal, but the concentrations are not. How can we figure out what the concentrations are, and how can we predict what's going to happen? Well, the idea of an equilibrium constant is what we've come up with to quantify the relative concentrations of reactants and products. So if we look at this generic chemical equation, where we have A plus B is in equilibrium with C and D, and we're using A, B, C, and D, lowercase letters as the coefficients to balance the equation. The equilibrium constant is the ratio at equilibrium of the products. So here we have the products, C and D, and putting those in brackets means that we have, that is the concentration in moles per liter. That's not what I wanted, which we haven't gotten to that yet, but we'll be okay. So concentration of C in moles per liter times the concentration of D, so it's the products, and then if they have a coefficient, it's raised to a power. So if C here was 2, that would be the concentration of C squared. Whatever C is, it becomes the power. The products divided by the same thing with the reactants. So we've got the reactants A and B. We're going to look at the concentration of A times the concentration of B, and it'll be raised to a power equal to the coefficient from the balanced chemical equation. So we need to know how to write these equilibrium expressions. So if we look at this reaction, 2N2O5 in equilibrium with 4NO2 and 1O2. Remember, we don't write the number 1 here because chemists don't like the number 1, and we discriminate against it regularly. Bless you. So we're going to take the products, NO2, put brackets around it, and O2, put brackets around it. The brackets represent concentration of this, what's inside. Here the coefficient is 4, and so this concentration is raised to the 4th power. For oxygen, the coefficient is 1. We didn't write it there, and we're not going to write it here either. And then the reactants are N2O5. There's only one of them, so that goes down here. And the coefficient was 2, so the exponent is 2. So the coefficients become the exponents. Do you see what's going on there? Kind of looks like a jumble of letters, but there's actually a pattern in there. Let's do this one. Write the equilibrium expression. So KEQ, that's the equilibrium constant, is equal to, we need to take the products, or product. What's the product in this reaction? HF. So I'm going to put HF in brackets. Is there a coefficient in front of it? Yeah. It's 2, so this becomes the concentration of HF squared. So all the products on the top and the reactants on the bottom. The reactants, we've got H2. What's the coefficient on hydrogen? 1. And so the exponent will be 1. We don't need to write that. And then we've got F2. And it also has a coefficient of 1 that's not written. And so we have an exponent of 1 that's not written. So that's the equilibrium expression for that chemical equation. Any questions? Yes?
Why was the other one different? Like, why was the other one where the product, I guess, was on the bottom?
No, the other one had the product on the top. So let's look at it. So these are the products, this one and this one. So this one had 2 products and 1 reactant. And so that's why there's 2 terms on top and 1 on the bottom. So it's going to be different from reaction to reaction, but the pattern is always the same. Any other questions?
My thought with left side of the reaction is always left. It's always on the bottom.
Yes. The left side, as written, is the reactant side, and the right side is the product side. So it's the right side on top and the left side on the bottom. Well, what does KEQ, that equilibrium constant, mean? If KEQ is large, like in this example, here's KEQ equals 1.9 times 10 to the 19th. That's a big number, right? That's 1, 9, and 18 zeros. It's a really, really big number. Well, what does KEQ represent? What's the equilibrium expression for that equation? It's the concentration of the products, there's only one here, HBr, with a coefficient of 2, so an exponent of 2, divided by the reactants, H2 and Br2. So if this number is a very, very big number, does that mean the top of this fraction is large and the bottom is small, or the other way around? It must be that the numerator is large and the denominator is small. That means the concentration of products is high and the concentration of reactants is low. You see that? So if this is...
The equilibrium number, is that always given?
The equilibrium constant is something that's determined experimentally, and it's not something you would memorize or just know.
So we wouldn't like figure it out with numbers?
Sometimes, though, what we'll find is if I give you these concentrations, you can calculate the equilibrium constant. But if you need it, we'll just give it to you. So if this is a large number, that means that the numerator is large, the denominator is small. And so that means that this reaction favors the forward direction. There's going to be more product and less reactants if KEQ is a big number. So if we look at the equilibrium constant, we can tell which direction is favored. If KEQ is small, like here's 10 to the minus 31. Is that a small number? It's a teeny, teeny, tiny number, right? What does that tell us about the relative concentrations? The reactants must be big and the product must be small, because here KEQ equals no squared divided by the concentration of N2 times the concentration of O2. And if this is a very small number, that means that the numerator is small and the denominator is large. These are the reactant concentrations. And so this tells us that the reverse reaction is favored. Yes?
So if KEQ is small, that means it favors the reactant all the time.
All the time. KEQ being small means this reaction doesn't go forward very much. It means that these product concentrations are very low compared to the reactant concentrations. When KEQ is large, the product concentrations are higher than the reactant concentrations.
So it means like they bump into each other more, creating more reactants?
It's complicated. At equilibrium, the rate of reaction forward and reverse is the same. So it's really hard to look at the rate of reaction with KEQ. You really can't do that. But this is going to tell us, he said, well, with these people running into each other, how many are going to have hands on their noses and how many are going to be normal? Is it going to be 50-50? Well, it could be, but probably not. How do we know? KEQ tells us. So KEQ being large tells us that we're going to have more product and less reactant. They're not going to be equal. KEQ being small tells us we're going to have more reactant and few product. And KEQ close to 1 or at 1 means it's going to be roughly equal. Yes?
I had a question. Is there something in that equation that's limiting the equilibrium? Because if the KEQ is large, as you're saying, it favors one. If it's small, it favors another. So what's limiting what?
Well, it's just a description of what actually happens. You can't just have any old concentrations you want here. You can start with these concentrations being pretty much whatever you want. The reaction does what it's going to do, according to the laws of chemistry. And then you can observe, okay, now I have these reactant concentrations and this product concentration, and that's how this actual number is calculated. You can't really make it be whatever you want it to be. There are things that you can do to affect it. Notice it says here at 25 degrees Celsius.
Right,
Sometimes if you change the temperature, the equilibrium constant will change.
right, that's one fact, that's one
Right.
way of doing it.
Yeah. But it's just our observation. And this idea of KEQ is just a way we came up with that seems meaningful to us to measure this. Maybe in 100 years they'll decide that there's a better way to measure it, but this is just what we've come up with. Any other questions? So here's pictures. Large equilibrium constant. I kind of already covered this, didn't I? If KEQ is a large number, that means we've got a lot of product and very few reactants at the end. And here's this picture. Here we see we've got one each of the reactant molecules and lots of product. KEQ being small is the opposite situation. Here are all of these that are the same color. Those are all reactants, and we've only got a little bit of product. KEQ is a small number. When KEQ is close to 1, we have roughly half and half. It's kind of in the middle. It's more balanced. And you're going to have significant amounts of both reactants and products. When these equilibrium constants are very small or very large, like the ones we looked at, 10 to the 19th, 10 to the minus 31, some of those, the amount of product or the amount of reactant that's small might be so small that you can't even measure it. And so it may appear that there's actually none of it there.